All right, welcome to day 2 of Unit 7. We're going to look at convergence and divergence as well as the nth term test today. There's your homework answers. You can pause here, check each of your answers, and then fast forward to the ones that you need to either look at the worked out solutions or hear me talk through. So DACB, all of them when you subbed in 1, you got back 4, so that didn't help you. So for 18, think of it as like a rational function, the horizontal asymptote, the ratio of the leading coefficients would be 8 over 1. So in 18, as n goes to infinity, that should approach 8. So that's why that one matches with A. In 20, when you put in 1, you get 4 over 1 factorial, so 4. When you put in 2, you get 16 over 2 factorial, so 8. So there's only one that's up at 8 at 2, so that's why that's got to be 20s has to be B. Now of 19 and 17, 19's exponential decay, so that should approach 0. And 17, if you think of it as horizontal asymptotes, the degree of the denominator is larger, so when n goes to infinity, that should approach 0 as well. So what I did is I just picked something like 3, because 3 in letter C is at 1, and 3 in letter D is closer to 2. So in 17, when you put 3 in for n, 3 plus 1 is 4, 8 divided by 4 is 2. So 17 must have to go with D, and 19 has to go with C. As n gets huge, the denominator gets huge, the numerator stays the same, so that should get close to 0. 45 would diverge because it's just going to bounce in between things. It will never approach anything. So that diverges. In 50, think of it as ratio of leading coefficients. They both have a leading coefficient of 1, so 1 divided by 1 is 1, so it converges. The numerator is going to bounce back and forth between things. Denominator will get huge in 52, so that approaches 0. So in 54, those both approach infinity. Do your derivative of each. Bottom's 1. Derivative of the inside over the inside, and then neaten it up. So you'll get a full n on the bottom with the 2. So 1 over infinity, so that converges to 0. Another way to think of it is the linear part, the n is going to grow much more quickly than the natural log part. So that will control the value of it. 56, that's just exponential decay, so eventually our terms will go to get close to 0. 58, that's n minus 2 times n minus 3 times n minus 4 dot 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 on top. On bottom you have n times n minus 1 times n minus 2 times n minus 3 dot 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 dot. So the n minus 2's on will divide out both top and bottom, and you're left with 1 over n times n minus 1. So the bottom will get huge. Top will stay the same, so that approaches 0. So remember in the exponent, the denominator is the root. So as n goes to infinity there, we're just taking huge roots. So if you take like the millionth root of 2, that's going to push it really close to 1. In 65, the top will just bounce between things. The bottom will get huge. That'll approach 0. Similar idea in 66. And that was it. So we're going to be on the day 2 notes in your notes packet. So some series AN So, sorry, an infinite sequence with an, if you add all the terms up, that is called an infinite series. So series is when we add them together. Sequence is when you just have a list of things. If an infinite sequence has a finite sum, then we say it converges. So if we keep adding terms and the sum looks like it's getting closer and closer to something, then we would say it converges. So in this first instance, we got the summation from 1 to infinity of 1 over 2 to the n. Well, let's write out a couple terms. If you're ever stuck in this unit, a good thing you can do is start writing out a few terms. So if we sub in 1, and that's a n equals 1 on the bottom there, it kind of blends together and looks like a n minus 1, but that's n equals 1. It's kind of small. So 1 over 2 to the first is just 1/2. 1 over 2 squared, we get a fourth. If we keep going, 2 cubed is an eighth. 1 over 2 to the fourth is 1/16th, and 1/32, and so on. So now the partial sums. S with a subscript is the sum of that many terms. So S sub 1 is saying, what's the sum of the first term? Well, it's just itself. What's the sum of the first two terms? Well, that's 1/4 plus 1/2. So that's going to be 3/4. The third partial sum is adding the first three together. So 1/2 plus 1/4 plus 1/8. So that's really 4/8, 2/8, and 1/8 to give us 7/8. S4 is just adding the first four. So that's 8/16, 4/16, 2/16, and 1/16 to give us 15/16. Well, let's see if we can figure out a pattern now. Our denominators are 2, 4, 8, 16. So that's 2 to the first, 4 to the 2 to the second, 2 to the third, 2 to the fourth. So the denominator is just 2 to the n. And notice the numerator is always 1 less than that. So that would be 2 to the n minus 1. Well, we want to know our limit as n approaches infinity. Well, when the numbers become enormous, like 2 to the million, 2 to the billion, that minus 1 in the numerator is going to have little to no effect. Those numerator denominators will essentially be identical, just off by 1, but when you're so huge, it won't be by much, so this will approach 1. So next up, we're going to show you how you can represent a sequence in several ways on the calculator. So first is from a list and spreadsheet page. So on our calculators, we can add a list and spreadsheet. We're going to call the top list. And we're going to put a formula in there. So notice it says column A there. So we're going to do SEQ for sequence. Start a parenthesis. First we put the equation. We're going to want it to count by 1, so we're just going to put x, comma, independent variable, which happens to also be x, comma, the starting number we want to sub in, so we're going to sub in 1. We'll do the first 100 terms, so that's the next thing, and then the step size, so 1. If you hit enter, it should generate that column all the way from 1 to 100. The next column we're going to call power. And our function that we had above was 1 over 2 to the n. So we're going to do it as 1 divided by 2 raised to, and then we're going to write list. So you can write out LAST, or if you do variable, which is above the 9, and select list, that's probably the easiest way to do it. So do 1 over 2 raised to, and only the 2 is getting raised to, and do variable, which is above the 9, and then list, and then that'll fill that all in. So then the last one, we're going to write partial sums. And I don't think they like spaces here. That's why we got to put it all as one word. And in the equals, in the formula, we're going to do CUM. That stands for cumulative sum. Start a parenthesis. And if we go to variable, we can go down to power, the thing that was in our other one, and hit enter. And notice it gives us those values that we had added up. Well, now let's do control doc, and we're going to add a graphs page. We're going to go menu and graph entry edit to change it to a scatter plot. In the X's, we want our list. So if we go to variable, we can select list. And in the Y's, what we're trying to graph is the partial sums. So we're going to do variable partial sums. So notice they appear to be leveling off at first look. But if you go to menu, trace, and graph trace, you can then just hit your right arrow and you can look at a bunch of them. Okay, notice it gets so close to 1. Okay, the calculator will eventually just round it to 1. It's not actually getting to 1, but it's getting so super close to 1. And that allows us to see what those partial sums are approaching. So that's sometimes called the infinite sum of that. So that's one way to do it. So if we go home and open up a new one, let's go to a graphs page. And in function mode, the typical mode, we can go sum sequence, SEQ, and we did something like this when we did Riemann sums. We could do parentheses, we can do the function that we want, so 1 divided by 2 raised to the x. Make sure to get out of the exponent, comma, we have to tell it the independent variable, so x, comma, the starting number we want to sub in, so 1, the last number that we want to go to, which we're just going to call it x, and then the step size of 1. So if we hit enter, if we go to control T, this will give us all of those in decimal values. So these are all the partial sums. And notice again, they're getting super close to 1. Now the last way you can do it, we're not going to go through it on here, but you can do it in sequence mode. If you go to graph entry edit and do sequence mode, we can get it that way and just do a trace for that as well. So those are all options. In reality, the best thing to do is just sub in a few things at the start and calculate a few of them, and that allows you to usually see where we're going. All right, so going back to our notes packet. So big distinction. If AN converges, remember AN is the sequence. That means the nth term has a limiting value. So if you list all of your terms out, the terms are getting really close to some number. But if your series converges, that means when you add up the terms, you get close to some value. So just a distinction about that, say you had a sequence, so you had a list of numbers. Let's say those were getting really close to 1. Well, that would be a converging sequence. But if you're to add those all up, you're going to keep adding on about 1, so then the series would not converge. So a sequence is a list of numbers. The series is if you're adding up all those terms, and different things cause them to converge. And we'll come back to that idea in a few slides. All right, so some different types of series. First one we're going to look at is a telescoping series. So we've got 1 over n minus 1 over n plus 1. We want to know if it converges. If it does, we're going to find the sum. When we sub in 1, 1 over 1 is 1. Minus 1 over 1 plus 1, so that's minus 1 half. Well, now we're going to sub in 2. So we'll get 1 half minus 1 third. We'll sub in 3. We'll get 1 third minus 1 fourth. We'll sub in 4. We'll get 1 fourth minus 1 fifth. Or all the way to the nth term, we'll have 1 over n minus 1 over n plus 1. Well, a telescoping series occurs when most of the stuff wipes out, so adds to 0. So negative a half and a half. Negative a third and a third. Negative fourth. Negative a fifth is in here. That will end up getting wiped out, and the last thing will be the only thing left. So we could express the sum as just 1 over 1 minus 1 over n plus 1. Right, so that represents our partial sum. So if we wanted the sum of the first 20 terms, we could do 1 minus 1 over 20 plus 1, and that'll be the sum of the first 20 things because most of them will wipe out. Well, now what about as this thing goes to infinity? Well, that fraction is going to go to 0, so this therefore is going to just approach 1. Now in general with a telescoping series, if you've got all these things wiping out, it'll always just be the first term minus the second part of the last term. So a1 minus your a n plus 1. So let's look at another one. Here it's not given to us as fractions, but we could do partial fractions to get that. So notice the bottom factors into n plus 2 and n plus 3. If we multiplied everything by the denominator, we would get 5 equals a times n plus 3 plus b times n plus 2. If we let n equal negative 3, we would have 5 equals negative b, so b is negative 5. If we let n equal negative 2, we would have 5 equals a, so that's where they're getting the a is 5 and b is negative 5. That then splits it into the two separate fractions. Well, now if we sub in, again, that's n equals 1, not n minus 1 under the summation. We're going to end up with 5 thirds minus 5 fourths. Then when we sub in 2, we're going to have 5 fourths minus, and I'm going to write it as 5 fifths just to keep the pattern going. Then we'll have 5 fifths minus 5 sixths. Then we'll have 5 sixths minus 5 sevenths. And in terms of n, the last term is going to be 5 over n plus 2 minus 5 over n plus 3. Well, this is telescoping. Once they all wipe out, we'll just have the first term, 5 thirds, minus the last thing, so 5 over n plus 3. And that represents any nth partial sum that we could be working with. As n goes to infinity, this goes to 5 thirds, so it would converge. And I guess I didn't specify here, but this does converge as well because it is going to 1. Now, not all your telescoping series will converge. Say we had n minus n plus 1, so no fractions here. When we fill in numbers, notice the negative 2 and 2 are going away, negative 3 and 3, negative 4 and 4, and so on. And we'll have 1 minus n plus 1. Distribute your negative, you get negative n. So your limit as n goes to infinity, that's going to go to negative infinity. So that one would not converge. So not every telescoping series will converge, but often if it's got fractions in it, it will. So telescoping is one type of series that we will see. It'll be not that common of one in reality compared to some of the others. So next up is a geometric series. You saw these in Algebra 2. Geometric is when you're multiplying by some common ratio, which we usually denote as r. Notice in this example, we're starting with n equals 0 on the bottom. So when we put in 0, 2 times 3 to the 0 is 2 times 1, so 2. And then the next one will have, sorry, I put that in the wrong spot. That is going to be 2 eventually also, but I wanted to put 2 there. When we put 1 in, there'll be 2 times 3 to the first, so we'll get 6. And then 2 times 3 to the second, so we'll get 18. And then it'll be 54, and it'll keep going. So the s's are our partial sums. The sum of the first term is just 2. The sum of the first 2 terms is 8. Sum of the first 3 terms is 26. Sum of the first 4 terms is 80, and it could keep going. So if we notice, this series is going to diverge because our partial sums seem to keep getting bigger and bigger and bigger. Well, let's look down at the bottom. We've got another geometric series. Now, geometric can be represented that they're in an exponential form, an a times b to a power. So here, when we sub in 0, we're going to get 4. When we sub in 1, we'll have 4 times a half, so we'll have 2. Then we're going to have 1. Then we're going to have a half, then a fourth, and so on. If we look at our partial sums, the first one's just 4. Adding the first 2 together gives us 6. First 3 gives us 7. Next one is 7.5 or 15 halves. Next one is 7.75, or in other words, 31 fourths. So those appear to be slowing down their growth. They keep getting closer and closer to something. Well, you might remember this from Algebra 2, but a geometric series will converge only if the absolute value of that r value is less than 1. If that r value is greater than or equal to 1, it will diverge. So in the top one, the r value is 3, that's why it diverged. Here our r value, what we're multiplying by over and over again, the 1/2, is less than 1, so it will converge. Now, you can find the sum of a convergent geometric sequence by that formula, a over 1 minus r. Now, in Algebra 2, they usually put a 1 with it, so a1 over 1 minus r. So we can find that sum here for this one. We would have a1 is 4 over 1 minus r, so 1 minus a half. Well, this is 4 over a half. And when you divide by a half, you're really multiplying by 2. So our sum would be 8. And if you look at our first 5 written out, it does appear that that is going to approach 8 if we keep writing out our partial sums. So a geometric series is going to be a somewhat common one that we will work with. All right, going to the next page, for each of these, we want to know if it converges or diverges, and if it converges, we're going to find the sum. So this is geometric because it's in an exponential form, but notice this r value, it is greater than 1, so this would diverge. And we would say our reason for why it's diverging, we would say geometric, and we would say r is greater than or equal to 1. Basically, this whole unit is telling if things converge or diverge and giving a reason why. So this one, we would say converges, since the absolute value of r is less than 1. And because it's converging, we can find the sum. So our a1, if we put in 0 for n, that'll be 12 times 2/3 to the 0, which is 12. Our r is 2/3, so this is 12 over 1/3, or in other words, 36 for our infinite sum. In 5, this one would diverge. And for our reason, we would say it's geometric. And the absolute value of r is greater than or equal to 1. I didn't put the absolute value on this one because for the greater than, if it's positive, you can just say greater than or equal to. But if we want to be consistent, we can throw that on if we want. Now, you might have to do some manipulation, like in number 6, to make something look geometric. Notice on top, 2 to the n plus 1 is saying 2 to the n times 2 to the first. So we can rewrite this as sum n equals 0 to infinity of 2 times 2 to the n over 2, or sorry, over 5 to the n, which can then be written as 2 times 2/5 to the n. So this would converge because it's geometric and the absolute value of r is less than 1. And because of that, we can find the sum. When we put in 0 for n, that first value, we'll end up getting 2. 2 times 2/5 to the 0. And we'll have 1 minus 2/5 for our 1 minus r. Well, that'll be 2 over 3/5. Dividing by 3/5 is the same as multiplying by 5/3. So for our infinite sum, we'll get 10/3. So in that series, if you keep adding terms, it'll get closer and closer to 10/3. Well, we can use geometric series to try and write a repeating decimal as a fraction. Let's think about what this is saying. If we have 0 in the tenths place, that's saying we have 0 over 10. 7 in the hundredths place is 7 over 100. Then we would have 2 over 1,000 plus 2 over 10,000 plus 2 over 100,000, and so on. So we would want to find, where does a geometric series start with that? So we want to look for when we're multiplying by some constant value. And where it's starting is from here on. So from that 2 over 1,000, we're then just multiplying by 1/10 each time to get the later terms. So what we can do is add those first two terms, and we get 7/100ths. So I'm going to write it as a fraction, because that's what we eventually want. Plus, now we're going to write this as a summation. So we're going to do n equals 0 to infinity. We want that first term to be 2 over 1,000. And then we're multiplying each time by 1/10 to get to the next one. Now, to ensure that 2 over 1,000 is the first term, we can just do it to the n, because on the bottom there we started with n equals 0. If we started with n equals 1, we would have to do it to the exponent of n minus 1. Well, we know that summation converges because it's a geometric with absolute value of r less than 1. So we can figure out the sum of this part by doing our first term over 1 minus our r. So that's going to be 2 over 1,000. This will be 9/10 on the bottom, so I'm going to multiply by its reciprocal of 10/9. We can take one of the zeros out by dividing, and this is going to give us 2 over 900. So if we bring it back over here, this means we have 7 over 100 plus 2 over 900. Getting a common denominator, multiplying by 9, this would now be 900. This would now be 63. So we really have 65 over 900, or that reduces to 13 over 180. And that would be that original decimal written as a fraction, and we use the geometric sequence to get there. All right, one last page for today. 2 slides, but one last page in your packet. So if you have some series and it's converging. So what that's meaning is we keep adding terms on, the partial sums don't appear to be going anywhere different. Okay, they're staying towards the same number. Then that means the sequence must converge to 0. So if the series is converging, if the sum is heading towards something, it means the terms you're adding on must be getting close to 0. So that means if your sequence values converge to 0, then the series, or do not converge to 0, then the series must diverge. And this is what's called the nth term test. Now, the nth term test can only show divergence. And the reason for that is if you show that a sequence goes to 0, that on its own is not sufficient to prove convergence. But if you can show that the sequence doesn't go to 0, then we know it must diverge. Because if you're adding on values down the line that are not getting small, then your sum is going to keep growing. So an example of why going to 0 for the terms is not enough is this series here, 1, 1/2, 1/3, 1/4, and so on. We're going to prove in a few days that this actually diverges. But that's an example of one where the individual terms go to 0, but the series will still diverge. So that's why just because the terms go to 0, you can't say it converges. So the only thing the nth term test can be used for is if the terms are not going to 0, then the series will diverge. So we're going to see if we can use that theorem here. Now looking at this is kind of interesting. Let's try subbing in some values. When we sub in 1 on top, we're going to get 1. On bottom, 1 factorial is 1 times 3 is 3, plus 5 is 8. Plus, if we put 2 on top, 2 factorial means 2 times 1, so we get 2. Well, on bottom, we'll have 3 times that 2 plus 5, so we'll get 11. Then 3 factorial means 3 times 2 times 1, so we get 6. So that n factorial on the bottom will be 6 times 3 is 18, plus 5, we get 23. If we do it for 4, 4 times 3 times 2 times 1 will be 24. And then that 24 times 3 plus 5 will give us 77. Well, notice 6/24 would be a quarter. So 6/23 is bigger than a quarter. If you had 24 out of 96, that would be a quarter. So 24 out of 77 is getting bigger. These values here are not getting smaller. So our limit as n approaches infinity of an does not equal 0. So we can say, therefore, it diverges by the nth term test. Now we really just need to know that the terms aren't going to 0. In reality, this is going to go to 1/3, kind of like our ratio of our leading coefficients, because as n gets huge, that plus 5 on the bottom isn't going to matter. So we can just do the 1/3 is approaching 1/3, even with factorials, kind of like we do with degrees. All right, for this next one, if we multiply it out, we're going to have an n squared minus 3 on top. And if we multiply out the bottom, we're going to have an n cubed and some other stuff. So our limit as n approaches infinity, by our leading coefficients, the denominator degree is larger. So this is going to approach 0, the value of our terms. So based on what we know, this may or may not converge. Because the nth term test can only show divergence if the terms are not going to 0. So if the terms are not getting small, then you're guaranteed it diverges. But the nth term test can't be used to show convergence. All right, in this next one, we can rewrite this if we wanted. Divide them both by 2 to the n plus 1. So this would be 2 to the n over 2 to the n plus 1 over 2 to the n plus 1. So really, our summation is n equals 1 to infinity. 2 to the n over 2 to the n plus 1, there's an extra 2 on the bottom. So 1/2 plus 1 over 2 to the n plus 1. Well, for our terms, as the limit as n goes to infinity of our terms, so the individual values, that second part of it is going to go to 0. So the terms are going to go to a half because there'll be 1/2 plus next to nothing. Because our terms are not going to 0, we can say that the series diverges by the nth term test. Now, if you haven't seen those 3 dots before in math, they're often meant to mean like therefore or in conclusion. So this diverges by the nth term test. So the nth term test can only be used to show divergence. If the terms are going to 0, well, then you've just got to find some other test. And we'll be learning other tests in the days to come. That's it for this video. Have a great rest of your day.